Welcome back. So now let's dive into how we can describe discontinuous functions like the one we were thinking about for our Morphine Administration example, and then how we can Laplace transform them so that we can actually use these as the forcing functions in ODEs. So the first discontinuous function that we're going to have a look at is called the Heaviside function. It's named after Oliver Heaviside, who you might well come across if you've done anything in electrical engineering, but also mathematics. He crops up in physics. He did a whole bunch of stuff. And the basic Heaviside function is very simple. All that we want to do with it is have something which describes a step function. So that's why it's also sometimes called the unit step function. So we want something that basically before t equals 0, so for negative time, our function is equal to 0. And then at time t equals 0, it has a discontinuity and it jumps up to a value of 1. And we use piecewise notation to describe this simple thing. So here we've got for t less than 0, it's 0, so that's less than or equal to, and t bigger than 0. So the only little thing to note is that there are many ways that you can define this, and the question is often, how do you define what the function is doing exactly at t equals 0? So we don't have any discussion about t strictly less than 0, that's always 0, and for t strictly bigger than 0, it's always 1. But there are different definitions depending on which program or which mathematics textbook you're looking at for what happens exactly at t is equal to 0. The relevant thing for you to know is that if you're using MATLAB, then at t equals 0, it sets the Heaviside function equal to 0.5. But for example, if you're using Mathematica, it sets it equal to 1. Maple, if you ever use Maple, leaves it undefined. It might seem kind of crazy that there isn't a fixed definition of what this is, but it turns out that actually it mostly doesn't matter, because generally we're integrating the Heaviside function, and when you're integrating, the value at one point alone doesn't make any difference. So it doesn't really matter. Okay, so it might initially seem like, well, it's a step function, what can you do with it? But you can actually describe pretty complicated functions using the Heaviside function. So for example, suppose we want to write this piecewise function, but as a sum of Heaviside functions. So what we're trying to do here is step away from piecewise functions, which make life tricky, because how do you integrate a piecewise function into something that is just described using a single line of coding or a single line of mathematics? So let's just sketch what we want this function to look like. So we want it to be 0, so the first bit, this bit, from 0 to 2, we want to be 0. Okay, so from 0 to 2, we want it to be 0. From 2 to 5, we want it to be equal to 3. So from 2 to 5, which will be somewhere over here, let's do this, we want it to be equal to 3. And you'll notice that I'm being a little bit careful here to use the correct open and closed circles, but don't worry too much about that. So that I should actually have marked in yellow. And then finally, for t bigger than 5, we want this to be equal to 0. So at 5, we're going to head back down to 0. Okay, so that's 5. Alrighty. So the first thing that we might think about is, well, let's just look at the first part of this. So we're just going to consider this first bit over here. And that looks almost like a Heaviside function, except we've shifted it to the right. So the first thing we can notice is that if we want to shift to get our transition from 0 to 1 at 2, what would we do? Well, we just say h of t minus 2. And that would give us something that looked like that. But the other thing to notice is that we want this to have a height of 3, and the Heaviside function is defined to have a height of 1. So we want to scale it, so we'll scale it by 3. So we get 3 h of t minus 2. So that is now giving us this thing. But now the question is, how do we tackle this bit over here? And the thing to notice there is that if you were to take the negative of the Heaviside function, then instead of going from 0 to 1, you would go down. You would go from 0 to minus 1. So we can use that idea to give us a step down function. So we can get a downward transition at 5. Well, what we want is we want to go down by 3. So we'll do the same thing. So we'll get 3 h of t minus 5. So that's shifted us all the way to the 5 and flipped us over. So putting this all together, we get our function. So we can write our 5t in terms of the Heaviside function as 3 times h of t minus 2 minus h of t minus 5. Which in some ways is not as easy to understand as this piecewise function, but when it comes to computations, it's going to be really useful to have a single equation that defines that function for us. Okay, so that's the basic idea of our Heaviside function, and you can imagine that you can build up pretty much any sort of step profile that you would like, with different magnitudes and stuff, by simply shifting and scaling your Heaviside functions and adding them and subtracting them as you need to. Okay, so let's bring this back to our original example, our morphine administration. So we were thinking about the regime where we had a patient after an operation on a certain amount of morphine, but at 12 hours they were like, no, the pain is really bad, and so the morphine was increased. So initially our patient is receiving 1.5 milligrams of morphine per hour, so this is a constant feed, and then after 12 it's 2.08. So we had something that looks like this. There's 12, and we have something like so, starting from time t equals 0, that's a 1.5, and then at 12 we increase to 2.08. And if you use the same techniques that we used in the previous example, what you end up with is, well, let's just check and see that this makes sense. So the first part over here is going to give us a function that does something like this. So it's like a little box. It goes up to 1.5 and it lasts from 0 to 12. And then this one over here is a function that goes up at 12 to 2.08. So we've added those two together, and then if you do the correct multiplication, seeing that you've got two terms that both have h of t minus 12, then you end up with our forcing function, which looks like this. So here is kind of a constant 1.5. So we're kind of imagining that we've got a constant 1.5 across over there, and then we've added on some extra for the last after 12, time t equals 12. So two ways of looking at the same thing. So now we can put this into our differential equation modeling our morphine absorption. So not a lot has changed. Here we've got the rate at which morphine is leaving the system, and here is our rate at which morphine is being introduced to the system. And this is now our discontinuous forcing function. And our initial condition was that we're starting off the person perhaps with an initial dose of 10. So they get given a single dose of 10 to just kind of see them over the initial waking up. Then they're on a drip at 1.5, and then eventually it increases after 12 hours to 2.08. So we have a differential equation. We've just been figuring out different ways of solving these using Laplace transforms. So we could take the Laplace transform of both sides, but the first thing that we need to be able to do is calculate the Laplace transform of the Heaviside function shifted for some constant c. So let's just do that, and this is actually going to be delightfully straightforward, so I'm not going to spend a lot of time on it. So we can work this out from first principles. So here we've just got immediately the definition of the Laplace transform. So we've got, don't forget, this is our improper integral, so we need to treat it with respect. The first thing we can notice is that we know that our Heaviside function is going to be 0 for times less than c, because we've shifted it to c, and so anything less than c is going to be 0. So the first thing we can do is we can change our lower limit to c, and that will, so it might be that c is positive, in which case it will kind of reduce the size of our integral, it might make it bigger, but we're only integrating from c. Okay, so that's not particularly interesting. The next thing we can notice is that either our Heaviside function is 0, but we're not integrating over that 0, or it's 1. So, and since we're only integrating over the values of t for which our Heaviside function is 1, we can just replace this with a 1. So that was pretty nice. So now we're just straight integrating e to the minus st from c to infinity, and that we can do using our usual improper integral routine. So you should do the whole limit as big T goes to infinity of the integral from c to t of e to the minus st dt. Not difficult at all. And the net result is this pretty straightforward thing over here. So the Laplace transform of the Heaviside function shifted to a t equals c is e to the minus cos over s. Okay, so that's pretty straightforward. So we can add that to our list of Laplace transforms. Okay, so now we can actually go straight ahead and calculate our Morphine Administration example. So just so that you've got it again, this is the ODE that we're solving. For an average human, our K is around 0.173, so that's about that's the rate at which morphine in the system leaves the system, so is absorbed or excreted. And our U of 0 being 10 says at time t equals 0 we give the person a single dose of morphine, as well as having them on the drip. Okay, so we do what we've been doing all along, so we take the Laplace transform of both sides. So if we look at the left hand side, Laplace transform of that, remember our Laplace transform of the derivative function is s of big U of s minus u at 0, so that's where this 10 comes from. And then on the right hand side we've got the Laplace transform of minus k times u, which is just this term over here, Laplace transform of the constant 1.5 will be 1.5 over s. Check the table if you've forgotten. And then we can use our newly discovered Laplace transform of the Heaviside function to get this term over here. Then we do the usual solving for our S-domain solution, and you'll get this if you do it correctly. And then if you were feeling super keen, you could use partial fractions, or you could just plug this into MATLAB, in which case you will find the somewhat hairy looking u of t, which looks like this. If you plot that, then you'll see that this is the function that we get. And it's worth spending a moment to think about, did we do something wrong? Could this be the kind of function that we're looking at? And if you think about it, it kind of makes sense. So we're starting off at time t equals 0. Our person has 10 milligrams of morphine in their system, and although we also have them on a drip, so it's a drip that's putting 1.5 milligrams per hour, nonetheless it's obvious that they are absorbing the morphine more quickly than the drug is being introduced by the continuous drip. So over time the amount of morphine is decreasing until presumably at this point over here the patient says, no, look, really I'm in a lot of pain, I need more. And at that point the drip amount is increased, and now because we've got the increased amount of morphine through the drip, that amount is bigger than the amount that's being excreted. So in fact the amount of morphine overall in the body is going up, and hopefully the patient isn't in pain anymore. Okay, so this does seem like it might actually be a fairly reasonable model. Things that you will notice, and we'll talk about this a little bit later, at this point over here it certainly looks like we're not differentiable. So one of the things I'll mention right at the end of this is, how can we say that this is a solution if there's to a differential equation if at some point it's not differentiable? But we'll talk about that later. For the moment we should just be kind of chuffed that we've got this solution that looks like it might actually model what we wanted it to. So let's move on to the final kind of example that we want to look at. So we were thinking about what happens if instead, for example, at time t equals 12, instead of giving the patient just an increase in the drip, so an increase in the continuous drip feed, what if instead at time t equals 12 you just given the patient a single injection? So something of the form, for example here, 0 everywhere except at time t equals t0 some positive amount gets added, or negative amount. We don't only have to think about situations involving drug administration. This, if we could be, for example, modeling a building and building swaying, and suddenly there's a gust of wind at a particular time, and it gives a single, like over a second or so, there's just a single bit of force, and after that it dies away. And again, we'd like to be able to model ODEs which have forcing functions like that. So in order to do that, we need another kind of function. So we've seen the Heaviside function. Now we're going to have a look at what's called, rather annoyingly, the Dirac delta function, but it is not a function. Not a function. But this won't stop people across the world calling it the Dirac delta function, and you will find that you do too. Sorry. But it's not actually a function. It's more generalized than that. It's called a distribution, or sometimes called a generalized function, or sometimes a measure. And if you want to study those, you probably want to go to grad school in maths, because there's a lot of fascinating stuff. But we can kind of get by with our notions of functions for the intuition that we need here. So the Dirac delta function, introduced by Paul Dirac, who you've probably heard if you've done any quantum mechanics. He popularized it when he was kind of needing it for quantum mechanics, but the idea of this kind of function, not function thing has been around for much longer, but it took a while for mathematicians to kind of really get it well described. So we're not going to do a super rigorous definition here because we can't. You need basically a different maths course if you're going to talk about this rigorously. But I hope I'll give you some intuition and you'll be able to use the idea of the Dirac delta in this course and any other courses where you encounter it. So the way we can start thinking about it, remember what we're trying to do is we want to describe a function that does something like at t equals 0, our function, let's just put this in red, our function is, for example, is equal to some value of k, and everywhere else it's equal to 0. So that would be the idealized function. So the way we can start to think about it is, let's take successive, so we know from our Heaviside function how to create functions that do, let's just do this a little bit better, do things like this. Okay, so we can use two Heaviside functions, we've seen how to do that, to create a kind of a little step up, step down function like that. So what we could do is we could think about modeling this crazy thing over here with a little step up, step down thing like that, where we decrease the width until it gets small enough that we're happy that we've actually just really got like this instantaneous up and down. So if you want to use Heaviside functions to model something shaped like that, where the width of this is epsilon and the height is a over 2 epsilon, and it's kind of positioned at point t0, then you can check, using what we did earlier, that this would be the function definition using the Heaviside function. So this gives you a little step of amplitude a over 2 epsilon, width epsilon, and centered at t0. It's not entirely clear at the moment why on earth you would want to have this, your amplitude as a over 2 epsilon. You're about to see now why we do. So whenever so if we're thinking about what we're going to be using our crazy impulse function for, we're going to want to integrate it. So what we care about is less about the function itself and more about its integral. So if we integrate our little step function that we created over here, then what we end up with after a little bit of work, because remember it's just a step function, is a. And that's why we define the amplitude of the original function the way we do, because actually what we're interested in is we want to specify what the area under the function is, and we want that to be a. So the thing to notice, if we plot, so here we've plotted for different values of epsilon. So we've got, in dotted blue, we've got epsilon is equal to 0.25, so that's this one over here. In green, we've got 0.1, so getting narrow and higher. And the key thing about all of each of these different rectangles is that they have the same area. So total impulse A is equal to 2. So although they have different widths and different heights, their areas are all the same. And although that might not seem intuitive, it is the most useful way to go about this, because we're caring about the integral of these functions more than we care about the actual function itself. Okay, so it might be tempting to think, well, okay, we want this kind of instantaneous up and down. What about if we were to take our little box function, and here we're looking at a simple example where we're centering it at 0 and our area is 1, so we've got our little function doing this. That's my dog waking up, if you can hear something shaking in the background. So we've got That's the thing that we're looking at here. And it might be tempting to say, well, we've done this before. What if we just shrink? So we've got our epsilon on either side. What if we just shrink epsilon to 0? So suppose we let the limit as epsilon goes to 0 of this function. Maybe we can do that. And if you do that and you plug in our definition here, then what you'll get is h of t plus epsilon minus h of t minus epsilon over 2 epsilon. And hopefully that rings a bell from calculus, and you'd be tempted to say, well, hey, look, that's just the derivative of our Heaviside function. And that might seem really great, like, wow, the Dirac delta is the derivative of the Heaviside function. Unfortunately, although intuitively it might be helpful, it's also nonsense. So why is it nonsense? Well, the problem over here is that if we have when t is not equal to 0, our limit here is defined. So that gives us a delta t equal to 0 when t is not equal to 0. So that's fine. That's what we want. Okay, remember we're trying to design a function that does this. But the problem comes when we look at what happens exactly at 0. Well, then you've got 0 over 0, and that's not defined. So if you remember from taking your limits, you'd have to do something to try and see if you can work it out, and actually it's not defined. So the problem with this kind of intuitive definition is that you end up with a delta t that is not defined at t is equal to 0, which is precisely the point that you would like to have it defined. And people tried many ways to kind of get to work around this and get a nice definition, but it turns out that actually you can't. So what you end up having to do is you have to define the delta function in terms of how it behaves within an integral, because that's generally where we want to use it. So that the actual definition, which we're not going to talk about a lot, relies on the behavior of this function, not function, within the integral, but there isn't an explicit definition for it without talking about the integral. What does it mean for us? Well, we're only ever really going to be caring about our delta function when we're integrating it. So for us, the key thing over here is that we think about the delta function kind of as the thing that's 0 everywhere except at t equals 0, in which case it's 1. That's kind of the rough idea that we have. But specifically, when we integrate it, it integrates to 1 if we integrate from a to b. Okay, so it's a little bit of a weird one. It's easier to see when we do some more examples. If we want to think a little bit more generally, because often we're going to be multiplying our delta function times some other function, for example a g of t, and just like with the Heaviside function, we're probably going to want to shift it, and we might want to have some amplitude. So generally, the kind of thing that we want to be able to answer is what is the integral of something like this? So here we've got some constant, some function, and here we've got a Dirac delta. And using the idea from the previous slide where we said, well, the Dirac delta integrates to 1, we can work out that our Dirac, if we integrate this thing over here, is defined like so. So here we have used this idea over here, we just haven't, have we done that? Yes, we have. So we're using that idea over there. The reason we can do that is we're not actually using the delta function itself, which is not defined. The delta function isn't defined as the derivative, but we can use this definition over here. If this is all seeming kind of weird, it is weird. The place that we want to get to is actually this equation over here, which is exactly what you might expect. Remember, our delta function just picks out the value of 1 when whatever's inside the delta function is equal to 0. So our delta function for example, delta t minus t0 is equal to 1 if t is equal to t0, 0 otherwise. So ignoring all the crazy definitions, what you would want to have happen is if you've got a delta function inside an integral and you've got some other function times a, then basically your delta function is 0 everywhere except at time t equals 0, where it's equal to 1. So what you should end up with, and which is why we've defined the delta function in terms of the integral, is you should end up with your function just evaluated at t0 times your constant. So if you take anything out of everything I've just been waffling on about, it's this formula over here, because this basically says your delta function does the thing you want it to do, which is pick out the value of 1 at t equals 0 and put 0 everywhere else. So it kind of gives you this impulse function that you're looking for. Okay, so this makes Dirac delta functions within integrals super easy to deal with. So if we have a look at this equation here, so we're integrating from 1 to 3, Dirac of t minus 2 times e to the t sine t. And you might look at that and go, I don't want to integrate that. But it's really easy, because remember, our delta function t minus 2 is going to be equal to 0 if t is not equal to 2, 1 if t is equal to 2. So it's a little thing that looks like this. So it picks out from within this integral the only time that the integrand there is non-zero is when t is equal to 2. So our solution here must be that this is e of 2 sine of 2. Now obviously we'd have a problem if the time that we were looking at where our delta function is non-zero doesn't lie within the range here. So 2 lies between 1 and 3, so we were fine, but you'd need to be a little bit careful if, for example, we were looking at the integral from 1 to 3 of delta t minus 5 e to the t sine of t dt. Well, within the limits of this, which is 1 to 3, our delta function is always equal to 0, so this would be equal to 0. Phew. Okay, so that's our delta function. It'll crop up all over physics. Read a little bit in the textbook if you're interested, but the key thing to take out of this is the intuition for, I guess, this part, which is what the delta function looks like, and this bit, which is how the delta function functions within an integral. So now we've got our impulse function. We need to obviously have the Laplace transform, because then we can use it to solve our ODEs. And we can plug straight into our original equation for the Laplace transform. So we plug it in. And we can use this equation over here, where we're taking our a is equal to 1, and our g is equal to e to the minus st, plug that straight in, and you get that the Laplace transform of our delta function centered at t equals t0 is e to the minus st0. If we're looking specifically at t0, so where our Dirac is centered, is at 0, then our Laplace transform is just this thing over here. So what happens in that case? So we have a is equal to 0 and b is equal to infinity, and g of t is equal to e to the minus st. So in terms of this over here. So now we can think about what happens if, so we need to think about what happens if we let t0 tend to 0 over here. And you can work this out. If you follow this through, you end up with the Laplace transform is just 1. So if you're looking at the Laplace transform of the Dirac delta not shifted, then it's just equal to 1. The Laplace transform of the Dirac delta shifted away from 0 is e to the minus st0, where t0 is where it's centered. Okay, phew. So finally we get to answer questions like this. So here we have a second order differential equation, and we've got an impulsive force of amplitude 10 happening at time t equals 1. So here we have basically a homogeneous differential equation everywhere except at t equals 1, when suddenly we get, bam, we get a force of 10, and then it dies away again. So let's have a look at what we get. Well, we just use what we know already from our Laplace transform for the left-hand side. So that's going to give us s squared u of s plus 2s u of s plus 10 u of s is equal to, and now we know what we've got, 10 times the Laplace transform of the shifted Dirac delta, so that's going to be e to the minus 5. You can check that. Solve this for big U of s to get 10 e to the minus 5 over s squared plus 2s plus 10, and do the usual either partial fractions or MATLAB, and that will give you u of t equal to 10 over 3 So what you'll notice about the solution over here is that it has a heaviside function in it. And it's a heaviside function which is centered at t is equal to 1, which is kind of what you'd expect, because you know that you've got something weird happening to the system at t equals 1, you've got the sudden impulse. So it's unsurprising that your solution has something changing quite dramatically at time t equals 1. This also kind of hints at the fact that even though we said that you can't define your Dirac delta as the derivative of the heaviside function, nonetheless, when we integrate, which is what we're kind of doing when we find the solution to an ODE, nonetheless, when we integrate the Dirac delta, we end up with a heaviside function. So there is intuition to be gained by thinking about the Dirac delta as kind of a derivative of the heaviside function, even though technically you can't define it like that. Okay, so finally back to the final case of our morphine example. So here's what we want to think about. Our R of t is going to be quite complicated. So we're imagining the situation that we had before, where we start out with an initial dose of 10, so a single dose of 10, and at the same time put the patient on a drip of 1.5, and now we're going to do something a little bit different. Oh, and we're also at time t equals 12 going to increase the supply like we did before to 2.08. But it might be that you don't want to slowly ramp up. If the patient is in a lot of pain at time t equals 12, you can say, okay, well, we are going to increase the amount from the drip, but maybe we also just want to give a boost so that the pain is managed immediately. So we're going to imagine that we give a very quick boost of, what are we going to do, of 5 milligrams at time t equals 12 as well. So here is the differential equation that or the impulse function that we've used so far, and now we're adding on this extra injection at time t equals 12. And we're keeping the same initial condition that the person gets an initial dose of 10 as well. And if we solve that, then what do we get? So you would just use exactly the same techniques that we've been doing before, and use MATLAB to do the inverse. What you get is a graph of the solution, and you'll see that what happens here, so let's just compare this to the solution that we got a little bit earlier. So the solution that we got earlier looked like this, and that seemed reasonable. But the problem with this might be that your patient is still going to be in extreme pain until we reach some threshold above which the morphine kicks in. And if a patient's in pain, they might be very tense, it's going to impede their healing. So instead, what you want to do is say, okay, we understand that you're in pain, and giving this extra injection at time t equals 12 immediately takes them into a happy place of pain-free. So you can figure out what this actually looks like, but you'll see that there are heaviside functions involved. You wouldn't be surprised. So we do have a discontinuity which might be worrying you slightly, but at the same time it's a discontinuity that we want to have, because if you think about what we're modeling, we should have an abrupt change in the amount of morphine in the system. So what do we conclude here? So as I mentioned when we first looked at the heaviside function, and I've just said again, when we're using heaviside functions and Dirac deltas, we can end up with solutions which are discontinuous at points. And you might say, well, how can we say that these solutions satisfy an ODE, which is defined in terms of differentiation, if you can't actually differentiate these functions because they're discontinuous? And the answer to that is you're right. And mostly you have to go and do kind of an advanced course to really think about these things. You'd learn about the theory of distributions and generalized functions. But for everyday applications, these things do what we want them to, and so we end up using them. Even though there's this kind of technicality of, like, that's not really the kind of function we want to be an answer to a differential equation because it's not differentiable. But it works. Phew, okay, so there was quite a lot of content in this. What do you need to know going forward? It's important to understand the heaviside function, so be able to use the heaviside function to put together step functions of all different kinds. Know how to find the Laplace transform of the heaviside function. You need to know the Dirac delta in terms of the Dirac delta of t is equal to 1 if t is equal to 0, and 0 is if t is not equal to 0. So that's a straight, simple definition. Or the Dirac delta of t minus t0 is equal to 1 if t is equal to t0, 0 if t is not equal to t0. So that's the piecewise definition. And you also need to know the Laplace transform, which we worked out, and the Laplace transform of the straight Dirac delta was equal to 1, and of the shifted Dirac delta oops, that was equal to, and now I'm going to forget, it was e to the minus st naught. So those are the key things that you need to know, and you need to know how to set up an ODE and solve it when we have forcing functions that might have discontinuous components. And in the back of your mind, you should be kind of pondering a little bit that we're getting these solutions which are discontinuous. They seem to model things correctly. They do what we would hope that they would do. And yet somehow there's this incongruity that we can't actually differentiate them. So how can we say that they're solutions to the ODE? Phew, okay. Practice some examples. I don't expect you to be able to do inverse Laplace transforms by hand. That's just crazy talk, except for the really simple ones where you can literally look up on the table and go, okay, well, my Laplace transform looks like this, and it came from a function that looks like that. So we did a few at the beginning. But other than that, I would never ask you to do partial fractions in a test or exam. So I will give you in a test or exam this table over here, or you can bring it in yourself, because you can bring in whatever notes you like. So here we have all the important functions that we've talked about, and they're Laplace transforms. So get used to using the table, because obviously you don't want to sit there integrating all the time, because that's just boring. And practice a lot of examples. We will have some examples to practice in the tutorial on Friday. All right, thank you.